Hello. We're the group Orbit Emulation and Machine Learning for enabling 5G and satellite network coexistence in the FR3 spectrum. I'm Chris, this is Aman, this is Parth, and this is Aadhil.
So for a brief overview on what our problem will be addressing, we'll be working in something called the FR3 spectrum, which is basically a range of frequencies starting from 7 gigahertz all the way to 24 gigahertz. And the benefits of this frequency range are that there's a large signal bandwidth and there's a strong signal propagation capabilities. And for this reason, satellites typically send data over this frequency range. And now, as demand for this grows, commercialization and research aims to have 5G operating in this range as well. However, one of the issues that arise is when 5G base stations and satellites are operating in the same frequency range, there can tend to be interference from the 5G signals. And because of this, a lot of the satellite transmissions can be cut off at the receiver and data will be lost. So our project aims to explore more about this, and we have created a model utilizing just 4 sensors and a machine learning model to predict interference at any location. And for a brief overview of how our experiment works, we will be using the orbit testbed, which consists of all these computer nodes on the ceilings above you. And with these nodes, some of them include something called software-defined radios, SDRs, which are basically components, radio components, that operate fully off of software rather than hardware. And we can use these radio components in order to emulate signals being sent from satellites and 5G signals as well. And on this image here, you can also see that we have a receiver moving around to indicate that we can detect in different locations.
So in order to manipulate the SDRs, we'll be using a software called GNU Radio. In GNU Radio, we can use open source software, and we can open source software, and we can create customizable blocks, and then we can turn that into sending and receiving signals on the actual testbed. Here we're going to simulate a satellite transmitter, a simple video transmission here. And can also emulate the 5G cell signal transmitter as interference. Signal overlap refers to the base station signal interfering with the satellite transmission. And here is a video of the interference happening in real time and the different interference scenarios we'll be looking at.
And as mentioned before, we will have 4 fixed sensors at each corner of our orbit testbed. And these sensors will be detecting something called fast Fourier transforms, FFTs, which is like a way of seeing the frequency components that each signal is comprised of. And in addition, we'll be having our portable receiver to collect data in different locations. And this receiver will have an SINR sensor, which is essentially the ratio of signal to unnecessary components, such as interference or noise. And we can measure this by detecting the signal power and all the signals that we send and calculating the SINR so that we can use this to train our machine learning model. Additionally, we want a way to measure performance of all the signals that we'll be transmitting and receiving. The first step was demodulating all the signals, and then we began constructing a bit error rate model, which measures performance by dividing the number of errors by total bits transmitted.
To emulate all these experiments on the Orbit testbed, we had to synchronize all these components and automate their processes. And to do that, we use bash scripting. So essentially, we have some files on our local computers, which perform connections with the computer of the Orbit testbed, and then the computer of the Orbit testbed connects to the transmitters, to the receivers, and to the FFT sensors, which write their contents into text files. And in each experiment we run, we varied the 5G sender frequency and the 5G transmitter gain. These connections are timed, the connections that we perform to each individual component. But the fact that they are sequentially turned on means that there are small discrepancies in the running time. So we need to find a reasonable time frame at which all of these components are up and running and average over that time frame to produce our measurements. We collected 3,000 measurements, and as said before, in each experiment, we varied the 5G parameters, but we also moved the moving SDR to 15 different locations underneath the orbit testbed. And that's how we collected data to feed to a machine learning model. So this is a general sketch of our neural network, and building up on what the R3 group said before. A neural network is a structure that can learn from data so as to make predictions and recognize patterns. So given an input, it produces an output. And in our case, the input is the the measurements of the four sensors at the corners for satellite transmission, the measurements of the four sensors at the corners for 5G transmission, and the satellite receiver location and the noise level. So this whole input is used to produce an estimated signal to interference and noise value at the satellite receiver site. What actually happens inside that network is that there's a separate mechanism that estimates the received satellite signal power using just the four measurements at the corners for satellite transmission. And then there's an equivalent block that predicts the interference level using this time the 5G measurements of the four sensors at the corners. So these two predictions signal interference and then combines with the noise level to produce the estimated SINR value. Essentially, since both predictors, signal and interference, perform the same task, we can focus on making one of them work, in our case, the interference predictor, to verify that the whole network works properly. Here you can see that interference predictor into some more detail. So it consists of 4 consecutive layers, and each layer takes the input, performs some mathematical operations on it, and feeds its output to the next layer. While the last layer, in our case, is the estimated interference.
We collect the location data of our receiver as spatial coordinates. So we face a challenge here because we collect the data only from few different locations beneath the test bed due to time constraint. There might be a chance that our model misinterprets and memorizes these locations instead of treating them like variables. So as a resolution, we decide to inject noise into our system. This means to introduce small random variations to our location coordinates. As you can see here, we introduce small random variations to get more data that's similar to 4. Evaluating our work, we classify a prediction is accurate if it falls within the 10% range of the actual power with respect to the total possible power range of a specific receiver location. Let's find out the accuracies in our case. For non-location, meaning the location the receiver has went through when it collected the data, the average accuracy for that is 91.44% specifically. This is a pretty good value, but that's not the case for unknown locations. For such locations where the receiver hasn't seen before, we got an average accuracy near 60%. Yeah, it's a bit low. But the reason behind that is that the data we give to the neural network is only from few locations. So our neural network didn't actually have a chance to identify how to handle XY coordinates of unknown locations. But this 60% gives a huge scope for future work.
So in conclusion, our model can accurately represent the interference at known locations. However, due to the sparse training data, meaning we haven't done many experiments on different locations, we can't track unknown locations. So if we want to improve the model, we would pretty much test at different locations. And for the future, we will be experimenting with different resource allocations, such as increasing the amount of base stations, receivers, and transmitters. Thank you.
Any questions? Thank you for listening.